Okay, last time we proved trig angle sum identities using triangles, using circles where you rotate and use the distance formula, and none of the proofs were particularly straightforward, I felt. So today, as I promised, I will show you how you can derive some of these results using just complex numbers and multiplication. So we're going to start by trying to find an identity for sine of 2 theta. And you probably remember what we're looking for here because you just did it a second ago in another way. We're going to start with a point A on the complex plane. So this is the real part. That's the real axis, the imaginary axis. This is the unit circle. So that's 1 and -1 and I and negative I. And A is some generic point at an angle theta. And its distance is 1 because it's on that unit circle. Okay, so what do we know about the coordinates of A? So that x-coordinate, which is the real part, has to be cosine theta. And the imaginary part, which you ordinarily think of as the y value, but here, remember, it's going to be the imaginary part of the complex number. So A plus bi, that would be the imaginary part, is sine theta. Because they're complex numbers, it's not an ordered pair. It's not two separate coordinates, but it's the real part plus I times the imaginary part. So a single number. Okay, so we've got A. Sine 2 theta must describe something about the point A squared. So pause the video. Think about what you know about the geometry of multiplying complex numbers. Think, where would A squared end up? Why does sine 2 theta describe something about it? And then actually multiply A times A. Multiply it out. Find what the coordinates are. And then ask yourself, what's this equal to? What's that equal to? Pause the video. Try it. I'm going to do it in just a second. Okay, here we go. So because when you multiply complex numbers, the angles add, if I multiply A by itself, A squared is going to be at an angle of theta plus another theta. So this angle now is 2 thetas. And if I drop a vertical line here, sine of this angle must describe the opposite side over the hypotenuse. But the hypotenuse is just 1. So this vertical side here must be sine of 2 theta. So far, so good. Okay, the visitors are gone. Meanwhile, let's figure out what the coordinates of A squared are. So I'll just multiply A times A. So that's cosine plus I sine times cosine plus I sine. So I'll just multiply each thing by each other thing the way that we do. So cosine times cosine is cosine squared. And then I've got cosine plus I sine and another cosine plus I sine. So that is 2 of cosine sine times I. And now I've got I sine theta times I sine theta, which gives me I squared sine squared theta. Okay, hopefully we have drilled into you that whenever you see an I squared, you think, what is that thing? Square root -1 times square root -1 becomes just -1. So this has now become cosine squared theta, 2 cosine theta sine theta times I, and then now this is minus sine squared theta. Okay, the last step here is we've got to group together the things involving I, which are the imaginary parts, and then group together the things that don't have I. Those are the real parts. So this has no I's, that has no I's. So those are the real parts. So I'll group those at the beginning. Cosine squared theta minus sine squared theta. And then I'll move the I to the beginning here. Let's put together the imaginary parts, which are 2 cosine theta, sine theta. You might be getting a familiar sensation when you see these two parts. But the question is why? Why are these so familiar? So these are the two coordinates of, or the two components of A squared. Sine 2 theta was that height. But remember, that height is the same thing as the imaginary part of A squared. So find with your eyes, where's the imaginary part of A squared? And there it is. So sine 2 theta by SOHCAHTOA describes that height, but that height is also 2 cosine sine. And there we've derived the identity. But we get another identity for free. Cosine 2 theta is that distance, again by SOHCAHTOA because it's the adjacent side over the hypotenuse. But that's the same thing as the real part of a squared. And the real part of a squared is that. So we also know that cosine 2 theta is cosine squared minus sine squared. So all we did was we just took a complex number, multiplied it by itself, and suddenly we have two double angle identities. Okay, see if you can use that same trick yourself to derive cosine alpha plus beta and sine alpha plus beta. Remember, this was the thing that took probably an hour. It took us like a half block followed by half of a Monday. And same thing for this one, and like two different groups. So there was a lot of effort that went into proving these things using triangles and circles. See if you can apply the same idea from the front side to derive these. Now I'm doing it. So A has the coordinates cosine alpha plus I sine alpha. B will be cosine beta times I sine beta. Because angles add when you multiply complex numbers, A times B will be at an angle of beta plus alpha. Let's find the coordinates. Here's here's A, here's B. I'll multiply it out. So I'll have cosine alpha times cosine beta. Here, I'm going to pause the video. Cosine alpha times I sine beta is going to give me I cosine sine. When I multiply these inner two, I sine alpha times cosine beta gives me this, and I can't combine them because notice the angles have reversed. So last time we could combine these into two, but this time they're different, so we can't combine them. And now very small at the edge of the paper, I have I squared times sine alpha sine beta. Okay, let's collect the real parts and the imaginary parts. Because I squared is -1, this is going to end up having no I, no imaginary component. It's just real, so we'll combine those two here. If you imagine factoring the I out of each of these terms, that's going to tell us the imaginary component. All right, we're ready to complete the proof. So the height here, the imaginary component of AB, is the same thing as the sine of alpha plus beta because of SOHCAHTOA. That's the same thing as this imaginary component. So that gives us cosine alpha, sine beta, sine alpha, cosine beta. Look at how little algebra we had to do. And we get the other identity also. Cosine alpha plus beta is that horizontal distance, which is the same as the real component. So that is cosine alpha cosine beta minus sine alpha sine beta.